record. Okay, and our speaker today is Dr. Ed Winter with RPI, and I'll let him introduce himself here in a moment. Everyone here is an expert now on using these, so send your Q&A through the preferably send it through the Q&A and not the chat, but I'll be monitoring both of those. And so once Ed wraps up with his presentation, we'll open up the Q&A. So Ed, I will go ahead and hand it over to you. Thank you.
Hi, how you doing, everybody? I appreciate you showing up today. My name is Edward Winter. I've been working for RPI now for about 5 years. Prior would be 5 years starting in January. Prior to that, I worked for the state of Kentucky. I came to work at the state of Kentucky as a toxicologist risk assessor and retired as assistant director. Prior to that, I was a postdoc at the Lyons Eye Center, where I worked primarily on calcium channels and diseases of the eye. And then prior to that, I was a graduate student. As a graduate student, my specialty was molecular toxicology. So a long background in these areas. Now with RPI, I do a little of everything, and about 20% of that is actually laboratory work. Okay, so let's get started on the presentation today. Natural source zone depletion and the activated carbon remedy, and what do those things have to do with one another? When you think about natural source zone depletion, in some sense, it's the same model as a risk assessment model. So you have a release. What happens to that release? Some of it is sorbed to soil. Some of it goes out in the vapor phase. Some of it gets into groundwater. And that which goes in the vapor phase may become a risk pathway to individuals, say, in buildings. That which is sorbed to soil might be a risk pathway for, say, an excavation scenario. And that which gets into groundwater, assuming someone's drinking that groundwater, would become a risk pathway through groundwater. But those are also all the same pathways of physical dispersion. And so we know that plumes don't grow forever. Why? Because they become sorbed to the soils and spread out in the groundwater, and then a certain percentage is lost in the vapor phase. So we will look at those aspects. But as you may well understand, that most of that comes into play early in a release. So you'll stabilize. So if you look at a release, if you have an opportunity to look at a release shortly after it occurs and you have enough monitoring wells in place, you'll see a very, very steep decline, which is physical redistribution of that LNAPL. Only later do you pick up a kind of a much shallower curve that goes on for a longer period of time, which is dominated by the biological breakdown of those components. So what is involved in natural source zone depletion? Sorption, dissolution, volatilization, and ultimately biodegradation. So most passive remedies, and that would include natural source zone depletion, are bioremediation. So if you're going to be successful, at least get natural source zone depletion in a period of time which most people think would be significant to control your risk pathways and useful to the environment, you've got to do it in a time frame that you can live with. So if you want to increase your biodegradation rates, ideally, you should buffer the total petroleum hydrocarbon concentration extreme. So you don't want those flexing up and down and up and down. Your dispersion helps you with that in quite a bit. So with the edges of your plume are where you get a lot of your degradation. But activated carbon can also help that. And it helps that by redistributing the contaminant mass on the carbon. You also need to disrupt the soil and aquifer materials. So that which is absorbed to the soil, if you're going to get it off the soil, you have to attempt some sort of active means. You need to provide electron acceptors. If you have contamination that is high enough to be of a concerning level, in all likelihood, you have an anaerobic environment. If you're going to biodegrade in an anaerobic environment, you need to respire with some kind of electron acceptor. Sulfate and nitrate are usually those that are easiest. You also have to deliver nutrients such as vitamins and amino acids. Most people don't think about this, but as an example from chlorinated solvents, you can have dihalocoides to break down your chlorinated solvents, but if you run out of vitamin B12, they're done. And it's not so different with hydrocarbons. You need folate, vitamin B6, and again, vitamin B12. If you run out of any of those elements, your biodegradation will drop, if not stop. You also have to balance your nitrogen to actual label carbon in order to get reasonable digestion. We'll cover that in a moment. And in some rare cases, in particular geologies, you might need trace minerals. Say, for instance, you might need magnesium, or you might need cobalt. These are important in certain enzyme reactions or in the enzyme itself to make it function. So let me talk about the carbon to nitrogen balance. When you have a release of petroleum hydrocarbon, it's not easy for bacteria to degrade it. If it were, you wouldn't really have a problem, right? So the carbon that's easier to digest, the label carbon, you need to have about 45 times that carbon in a molar ratio to dissolved nitrogen. If the dissolved nitrogen is actually much higher than that, it will hinder biodegradation. Now, this is not usually thought of because most people model what they think they need in nitrogen from agricultural fields, but most of the carbon in an agricultural field is labeled. So it's kind of hard to put too much nitrogen, but you can. And you certainly can with biodegradation. So you have to balance the amount of nitrogen you give. So this is kind of the little commercial part, the cost of listening to a presentation, I suppose. But we have two products that will help with biodegradation and provide activated carbon, which helps distribute the contaminant mass. The older product and most well-known is the Boss 200. It's powdered activated carbon. It's supplemented with electron acceptors, nitrate, sulfate, very small amount of iron, and microbes. The microbial mix includes bacteria, yeast, and fungi. Boss 200 adds supplemental nitrogen, and we had to figure out how we could do that. And we actually add supplemental carbon. And that carbon, with that carbon, we add additional microbes. And the point of those additional microbes, in part, is to break down that carbon so you have a higher label carbon element, allows you to put in a larger nitrogen element, and also allows you to build a much larger microbial community that's more robust against LNAPL. So the carbon element itself, what would that be doing for you in natural source zone depletion? Well, as I mentioned earlier, you're going to buffer the TPH concentration extremes, because while microbes can degrade hydrocarbons, there is a sweet spot where too low or too high doesn't get you your best degradation rate. So to be able to distribute over an area and get those concentrations about where you need them increases your degradation rate. So you can think of this as physical redistribution, except the activated carbon is more like a high rise, like you've just filled it full, as opposed to spreading it out across the open areas like a suburb. And then, as I've mentioned earlier, also the edges of these concentration changes are sometimes the best places for higher rates of biodegradation. So that's what we're looking for with the activated carbon. So we're not just absorbing it though. Activated carbon also desorbs. And this is an important aspect to consider. So when you put activated carbon in the ground, you're not just putting these sponges that suck up your petroleum hydrocarbon and never let it go. If you have a concentration, and you can see this on the left side table, if you have a concentration of 10 parts per million of benzene, the capacity of the carbon is 40 milligrams per gram. If your concentration in the groundwater is 1 part per million, then your capacity on the activated carbon is 1 milligram per gram. The same is true for ethylbenzene, naphthalene, various alkenes and polyaromatic hydrocarbons. It's all the same. What is bound to the carbon is balanced against what is in the groundwater. So if you reduce the amount in the groundwater, the activated carbon will then slowly release that hydrocarbon into the groundwater to, again, get this balance. That allows you to pull hydrocarbon into the activated carbon, but it also allows that activated carbon to come off as biodegradation proceeds. It's not the only thing that happens in biodegradation, but this is an important aspect of the physical characteristic of activated carbon. So, activated carbon participates through physical redistribution, through sorption, and finally through biological breakdown. Bacteria like activated carbon. They adhere to activated carbon. They reside in the large fractures and large macropores, are the niches that maybe one might think of. And finally, as this biodegradation occurs, one easy way to follow it is look at the dissolved gases. Now, I don't have a presentation on dissolved gases today, but if you have some interest in that, let me know. Okay, so the picture on your right-hand side is of a carbon diesel bench. And what I want you to see in this picture is how the activated carbon is kind of adhered in a blob. And if you look closely, you can actually see a film, and that's biofilm. This is where the microbes have built up on the activated carbon, and they're kind of holding that carbon together so that the diesel in the carbon is acting as a feed source at the same time that the activated carbon is acting as a substrate for microbial growth. This is important because if you look at most geological materials, and I can't say all, haven't looked at all, but if you look at most geological materials, they have a limit to the number of microbes that can grow on that material. It's the material itself that is a question. So if you look at the picture that I have up now, on the bottom of the picture, you see clay. And as you move over time, you can see some microbes growing on the clay. I've circled them with red. So initially you have almost none. I can catch a few in that first picture. In the second picture, very hard to find, but I found one and circled it for you. As you go to the third picture, which is the one that I'm moving left to right here, the third picture, you can see a microbe that I've got circled. And if you take that as an example and look around, you'll see quite a few more. Looking at the top picture, that is PAC. So that is powdered activated carbon. And you can see these pictures are all on the very same time frame. Already in the very first picture at 4 days, the same as it was for the first picture in clay, you are covered with bacteria. And you just see it increase 6 days and 11 days. So by the time you get to 11 days, it's a field of bacteria. And you will see that activated carbon seems to support microbial growth pretty much better than any material that I'm aware of. And this is important for you. Why? Because your microbial community is not made of just biodegraders. It's made of other microbes that support biodegradation. They may be producing fatty acids relative to fermentation. They may be producing some of the vitamins that we mentioned earlier. And many microbes cannot make all the amino acids they need. They need helpers to do that. So the larger the microbial community you get, the greater your biodegradation rate is going to be, not only because of the increased numbers of degraders, but the increased number of helpers in this degradation process. There's also a process, kind of a side note here, in which more microbes, almost regardless of what they are, increase biodegradation. And that's through very, very common pathways, such as the glutathione pathway and P450 pathways. But that's for another time. If you have an interest in a presentation like that, let me know. So here's a great picture. This is a live dead stain of activated carbon with bacteria growing on it. And the green dots are live bacteria. The red dots are dead bacteria. And thus you see this film on this activated carbon. I just like the picture, so that's why I'm showing it to you. Here's another picture, similarly, that emphasizes the importance of activated carbon and activated carbon of a particular kind. We'll start with the picture on the right first. This is Warren Kinzierski. He did this picture. It's at a slightly lower magnification than the one on the left, but this is a pore in activated carbon, and you see that the pore is full of microbes. Note that around the edge, there's not really much growth. Now, the picture on the left is my picture, and I will tell you right now it's colorized because electron microscopes, everything is black and white. So I colorized it so you could see things better. But one of the things you'll immediately note is that there's almost no growth on the surface of the activated carbon. Almost all the growth are the red and yellow microbes that I marked in the pit. And this is what you will see when you look at activated carbon, that the pits and the crevices are filled first, and they're filled most abundantly. If you look down on this electron micrograph that's on the left, look down on the right-hand side of that picture, you'll see a scale there that says 5 micrometers. So that gives you an idea how big this pit is. This pit's probably 10, 15 micrometers across and that much tall. You'll also see that the microbes themselves are, roughly 3 micrometers. To the far right in this picture, the yellow material is yeast, actually. So this will give you an idea of how, or give you an idea of what it looks like for microbes to prefer activated carbon of a particular size, and prefer the pits in that activated carbon. Now, what will happen if you give activated carbon of a much smaller size? It just takes a lot longer for the microbes to grow, and eventually what they'll do is they'll start pulling those pieces together, in a sense trying to make their own larger piece. Okay, degradation rates. Now this is out of the ITRC document from 2018. And this seems like it just popped out of nowhere as a topic, but it plays into what I'm going to show you in the following slides. And what's going on here, they have clay, 2 different kinds of clay with the blue line and the green line, and a silt with the orange line. And that's what most of us end up working with. Sand and gravel is not really that relevant. Now, if you look up on the y-axis, you'll see depth to the aerobic anaerobic interface. So 10 to 20 feet is about 3 to 6 meters. And what do you see the hydrocarbon degradation rate being? It's roughly 0.4 to 3 grams per meter squared a day via natural source zone depletion. So you can kind of keep that in your mind almost as a control, okay? It's out of people's own studies, it's out of the ITRC, so there's some variability that you might expect, but 0.4 to 3 grams per meter squared a day. So first we're going to talk about some bench testing. And I know that most people would rather see field results, but you do these bench tests in order so you can focus on particular aspects of what you're trying to develop in a product. So we're going to vary electron acceptors. We're going to add carbohydrates. We will modestly in this particular study look at a couple different carbons, and we're going to vary bacterial blends. So here's a bench test where we're looking at electron acceptors. So in this particular case, we've got coal-based carbon. We did wood-based carbon also, but I'm not showing you the graph. So the coal-based carbon, when we allowed diesel range organics to bind to the coal-based carbon, it absorbed 58% of its weight, where wood-based absorbed 29% of its base. 29% of what was provided to it. The electron acceptor choice, we will see matters. This test was run for 4 months. And we're going to look at the addition of additional carbohydrates. And in this particular test, all the microbial mixes were the RPI microbial mix for this particular picture. So what do you see with all those things being true? If we ask ourselves, if we only give it nitrate as an electron acceptor, that would be the bar graph that is in the middle of your screen. You see that benzene degradation doesn't occur. A minus 3% is the kind of error you might see in these kinds of measurements. It doesn't mean anything. You see that hexane degradation is 82%, and total volatile petroleum hydrocarbons is 72% degraded. A surprising result, actually, because most people think that benzene degradation is most often related to nitrate. And that is true, but you have a particular microbial mix, and that's fixed for this study. It's not as true, though, as you might think. The next graph over to, as you move to your right, is mixing nitrate and sulfate. So you've got the dual electron acceptors over this 4-month test. And in this case, you see 55% of the benzene is degraded. You stay about the same with the hexane. You do a little bit better with total volatile petroleum hydrocarbons. The next bar graph, which is on the far right, includes nitrate, sulfate, and complex carbohydrates. And in this case, you see all of them do much better. So you think, okay, so we need no sulfate, nitrate, and complex carbohydrates according to this particular study. So what about the microbial population? So what we did was compare the RPI culture, which is the first bar graph on the graph that's being shown, so the one on the left, to 3 commercial cultures. And what you see is that 3 of the 4 blends perform pretty well. I would say that given the error in the test, that the RPI culture and culture 1 are pretty much performing the same. Culture 2 maybe slightly less, and culture 3, well, yeah, it's not as good. But interestingly enough, it seems to be very good for the total volatile petroleum hydrocarbons. So what do you learn here? Well, as a marketer, we want you to see that our culture is good, and it is. But you also see that different cultures have somewhat different results. So the culture matters. Now, this is a really interesting study and kind of takes you a minute to think about what it is we're showing you. So earlier in the previous slide, I was showing you that we absorbed diesel range organic to the activated carbon, and then we went through some biodegradation tests. So in this particular case, we absorbed the petroleum hydrocarbon to the activated carbon, and we found, if you look at the far left bar graph, that 98% absorbed to the activated carbon. And you'll see that in the center graph and 92% on the other one. So what is this? This is the amount that was initially absorbed to the activated carbon, in the case to the far left, when we had nitrate added. So that was our base. Then we let it biodegrade. The same with each of the others, where you look at the orange bar. You absorbed it, and then later we let it biodegrade. But all you're seeing on that orange bar is what was initially absorbed. What you're not seeing is then we let it biodegrade for 6 months. After we let it biodegrade for 6 months, that was similar to the previous test you saw, we said, I wonder if we can respike these same samples. And we did. We respiked it with 500 parts per million. In this case, for the volume that we will work in, that would be 75 milligrams of gasoline. We let it sit for 2 weeks and then did the analysis again. And what did we find? We found that in that which had nitrogen only, that was the base that we started with, we had 54% absorption. With the activated carbon and nitrogen and sulfate, we had 86% absorption. When we added the complex carbohydrate, we had 93% absorption. So now, probably I should give you a picture of this, but here's what I want you to imagine in your mind. You had this carbon, and you had, stick to the far left, you had nitrogen in with it, and then you looked and said, determined, how much was absorbed. And you put that down at 98%. Then you added the microbial mix, and you waited and waited and waited for the 6 months period of time. What is happening during that time? You're building up a biofilm on that activated carbon, and those microbes are degrading the petroleum hydrocarbon. And you're waiting. And so then you come back and you have carbon with a biofilm and very little petroleum hydrocarbon left. And you respike. And what happens with that respike? You see, you get different rates of absorption, and some biodegradation. The gist of this experiment, what we were trying to get a sense of, this is not proof, this is just a sense of, does the microbial population that builds up on the activated carbon, does that prevent absorption? And what you can see is, assuming that population was a good degrading population to begin with, remember the nitrate alone was not, but the nitrate and sulfate was, the nitrate, sulfate, and complex carbohydrate also was, you see that that population also restores the absorptive capacity of the activated carbon. So you can see that happening. The microbes on the carbon, they're in a sense, pulling the hydrocarbon off the carbon so that the carbon now has more absorptive space, and you can do this again and again and again. That was what is illustrated, both shown and illustrated by this experiment. So what is the degradation rate of diesel range organics over time? It's about 0.5 milligram degraded per milligram of activated carbon. 0.5 milligram per milligram of activated carbon. Now, this is a case study. And this particular site was in Texas for what it's worth. I don't know that we'll say much else about it, but that it was if you look to your right, you can see a big circular thing there. That's an oil storage tank. So this was not a minor release. The red lines that you'll see in this picture and in some other pictures are pipelines. So we took 1,110 soil samples to actually determine what the mass of the contaminant bound to the soil was and how that was distributed. Those sample results were used to determine what the activated carbon loading should be in design. And of course, all the samples were analyzed at the RPI lab at no cost to the client. So these are two different areas of the site. I showed you one area. Here's another area. And this area certainly illustrates all the pipelines that are running through the site and how we had to stay 10 feet off the pipelines. The different color areas represent areas where we injected, and the areas were injected at slightly different concentrations of activated carbon depending on the amount of contamination in the area. So the treatment area in the particular example that I'm giving you now was 8,650 meters squared. The lithology varied across the site, but it was mainly a silty clay to clay over weathered shale. There's some sand and gravels. The depth to water was 1.5 to 6 meters below ground surface. It varied across the site. The contaminants were LNAPL, TPH, and benzene. So essentially, the technology was the BOSS 200, which included the activated carbon, the sulfate, the nitrate, the complex carbohydrates, additional nutrients, and bacteria, all the elements that are required for biodegradation. The implementation method was a little bit different. It's called pre-drill. And that was because you had a lot of weathered shale and things like this. So you drill through the shale, you backfill the hole with bentonite, and then you can use your DPE to push back through the bentonite and inject in that manner. If you've ever had anyone present you a similar injection where they actually cut through PVC pipe, it's something like that. What were the results on this site? And I should have mentioned that it was a free product site because that's part of this whole presentation, is that as you look over time, you see both the benzene and the TPH drop precipitously. So your control is right there at the beginning of the graph on day 0. And you lead from that with the injection. You'll see the TPH jumps, the benzene dives, comes back up. This is kind of typical in the initial phases of equilibrating to the activated carbon. And you see this graph continue to day 1,800. And you can see the result here. So this was not just like I cut it off, in the first year. I can't say now, well, maybe it'll wait for the next picture. Okay, this particular one, you see benzene and sulfate. So you see that we put the gray line is sulfate, the blue line is benzene. The benzene concentrations drop significantly. And you'll see that there was enough sulfate installed that we still had sulfate available once the benzene was largely degraded. This particular graph is really meant more as an illustration than anything. So the total number of wells with measurable LNAPL on this site were 15 wells. Post-remediation, we had no measurable LNAPL in 12 of the wells. You had a sheen on 2 of the wells, and 1 well had measurable LNAPL. And part of the reason it did is because we weren't really allowed to inject anywhere near it. It was too close to a pipe. It was actually triangulated by pipelines. So, there was really no ability to treat immediately in that area, but it has still dropped. And presently, this site has been approved for regulatory closure. So the results of natural source zone depletion degradation rates. Remember, we said that the ITRC document lists this as 0.4 to 3 grams per meter squared a day. We estimate the rate from this particular site at 13.8 grams per meter squared a day, or 5 to 30 time increase. Let me show you a different site, because that's a big tank farm kind of site. A lot of you work on things that are more like UST sites. And so this is a site that had free product, not like the previous site, which had feet of free product. This had, maybe an inch here or there, and largely is a sheen as far as the monitoring wells go. Of course, that oftentimes indicates a much larger amount of free product than the wells tell you. In this particular case, what I'm showing you is the ethylbenzene post-treatment that we're measuring in aquifer soils at 30 months. So our concentration initial on the left side are the blue dots. And you can see, we took a lot of soil samples, so many of the dots are basically 0 for both data sets. But once you get up into the higher concentrations, you can see how the two graphs vary from one another. The red dots are post-injection. Now, because someone will bring this up as a question, you can't collect the same soil sample twice. So in order to actually see degradation in the soil, you really have to take a lot of samples. Once you collect a sample and send it to the lab, even of that sample, a very, very small amount of that is actually run. And even a clean site, if you run enough soil samples, you go from basically being a black dog, not to a white dog, but to a Dalmatian, because there will remain little spots of contamination that you just can't get rid of. You haven't been able to disperse it in some manner, or get microbes to it, or absorb it, or any of those processes. So you end up with this Dalmatian kind of return. Now, in this particular case, we had 120 samples. The distinct observations range from 115 to 9. And what I really want you to look at, you can go through all these numbers on your own. You'll see the mean dropped by roughly half. The median dropped by about 75%. You can see the standard deviation dropped. But the p-value, the difference between the probability of actually reaching into that sample if I were given an opportunity again, and finding out that the two samples weren't actually different, the probability is 9.38 times 10 to the 4th. This is a very, very small number. So you would reject that as your hypothesis, and you would conclude that these two samples are very different. And that's the point of this picture. And we have this for benzene, xylene, naphthalene, etc. And putting that together, what did we find at this particular site injected, in this case with BOSS 200 at 30 months? We found that benzene was 3.6-fold lower. The significant difference between the two data sets was 0.009, means the chance that I've guessed wrong, that's how small it is. And the half-life is roughly half a year. The toluene, 1.5-fold, another very small p-value. The half-life is 1.16, and you can follow this through the chart. In each case, the median difference was lower, the p-value is significant, and the half-life is recorded. But what you don't really know right off is, well, so what? What's that half-life compared to? So on this particular chart, I've put the constituents on the left-hand side. The half-life is the next column. Now, the next column is the Kentucky estimates using groundwater. So Larry Hughes and I, years ago for the TANKS conference, I think it was the 2013 TANKS conference, we figured out from the state database what the estimated half-life would be for benzene. And it's 3.2 years. And then we did BTEX. I think we actually did these other constituents. I'd have to go back and look at the data and see. But nevertheless, BTEX as a whole was 3.9 years. There's a published California study by Tom McHugh and company that shows in California, no action, you haven't done anything. What's the half-life? It's 3.8 years. Wow, it's not so different, despite the fact that the geology is very different. The benzene half-lives are very similar. And if you take the average of the toluene, ethylbenzene, xylene numbers, the average is 3.9, the same as Kentucky's average for BTEX. So that's very interesting, the half-lives of a no action for both California and Kentucky, to the data that we have, are almost the same. And then look at those numbers and compare them. The benzene half-life from the site I just showed you is about half a year as opposed to 3.2 years. The toluene is a little more than 1 year as opposed to 3.2. Ethylbenzene is a half year as opposed to 4.6 years, etc. So what we've shown you on two different sites, one of them a large tank farm in which we showed you that post carbon injection, you have a much higher degradation rate. And this I showed you from a small UST site and actually have the numbers and the statistics to back it up, that we have significantly moved the half-lives. So in summary, what does activated carbon have to do with natural source zone depletion? Natural source zone depletion in the end is biodegradation. Because after the initial dispersion, what do you have? Biodegradation. And activated carbon can be used to enhance that biodegradation through a number of means, such as increasing dispersion, increasing edge effects, increasing the number of microbes that are actually in the area and degrading. Different types of carbon, I didn't show you so much of this other than the wood carbon, have different absorption capacities. I will say that different activated carbons support biodegradation at different rates also. The bacteria themselves from the diesel bench we showed you can regenerate the carbon in situ to provide a long-term remediation strategy so that you don't just load the carbon once. You load the carbon, the bacteria will change the environment and the manner of the carbon as they degrade the contaminant, and will allow the carbon to reload, and this strategy will continue until finally biodegradation of the entire mass of contaminant has occurred. The limiting factor is your long-term electron acceptors. We showed you from the Texas oil tank site that we had degraded the benzene and we still had sulfate left. And I should mention that it is the proper ratio of terminal electron acceptors, because we talked about that, having the right amount of nitrogen to label carbon. To be able to do this and be successful, you need to have a proper conceptual site model. You have to understand the mass of contaminant actually bound to the soil, so that you know what your loading is, so you can figure what your biodegradation rates are, so that you can project forward and where you need to be. And I should say that also affects your loading as far as your terminal electron acceptors. So I hope you've appreciated the presentation. I'll take any questions you have now, Mike. It's to you.
Thanks, Ed. So we've got about 15 minutes. We've got a couple questions that have come through already. So if you've got any for Ed, please go ahead and fire those through to the Q&A. So we'll go ahead and start. How much, Ed, does the hydrocarbon fraction itself impact impact this. So let's just say, TPH, GRO, DRO, F1, F2, that sort of
Yeah,
thing.
some hydrocarbons are clearly harder to degrade than others, right? So your rather small alkenes are rather easy to degrade. Some of your aromatics, I mean, any of the regulators on here, well, heck, all of you know that benzene tends to drive because of its toxicity and its difficulty of degrading, tends to drive your sites. They tend to drive your risk scenarios. And then when you get to really large hydrocarbons, a lot of times the ability for them to move off the soil or anything they're glommed onto becomes a little harder. And so they're also harder to degrade. It's that middle range that degrades fairly well. The how much of that you have in one place, when I was talking about dispersing the contaminant a little bit or putting it onto the carbon, that helps. Obviously, a glob of very high molecular weight hydrocarbon to which you've done little dispersion and for which you have a hard time getting water into the glob or microbes, etc. That's going to be very hard to degrade. I hope that's the question.
Yeah, I think that answers it. Another one about recommended upfront microbiological testing and whether or not that's something that you recommend. Can you comment on that?
That's a good question. Things like next gen sequencing have become very cheap, and it is interesting to know. Do you have to know it? I don't think so. I don't think you have to. I want to. So if you're going to send those results to me, here I am. I'll love to have them. But no, I
Mhm.
don't think it's an absolute requirement. But if you're looking at a geology and you have some reason to believe that biodegradation is a problem in that geology, a problem for that site. Let's say someone has used a remedy prior to the remedy you want to use now that has significantly changed the pH, as an example. It's just off the cuff. You might want to look at the microbial community and think about, is this community balanced? In some cases, you can end up with a community that's very unbalanced because of actions that have been taken or the contaminant itself that was released. And you might want to augment that community, and you might want to know how to do that. But in most cases, what we try to do at RPI is with the BOSS 200 Plus, we are introducing probably close to 50 microbes. And we know that many of those microbes will die. They just won't make it. They'll become food for other microbes. But a
Mhm.
few of those microbes will fill a niche that is a little weak on that site. And it won't be the same niche for every site.
Mhm.
Yeah.
Okay. All right. Is there a free product threshold above which you would not recommend BOSS 200 or BOSS 200 plus?
I guess the answer is first, no. It's not really important. I would I would say just for your own sake, you may want to look at that site and ask yourself cost per effort. Do you want to take some initial action to
Mhm.
remove some of that free product? In some case, dual phase extraction can be very, very useful. But
Mhm.
as the question was asked and as it stands, no, there are microbes that live within free product. When you pump oil from the ground, crude oil, there are microbes in it. Now, they're not degrading a lot of it, otherwise, we wouldn't have any, right? But they are able to live in it. And if you provide the right support, you will increase the number of microbes and they will degrade whatever hydrocarbon you have. Matter of
Right.
time, matter of cost, matter of looking at what your priorities are for a particular site.
Yeah, and I can add to that as well. We've performed several sites and we're looking at several others where we're doing they obviously depend on geology and whatnot, but especially for heavier hydrocarbon sites, looking at using something like surfactants, and that kind of ties in with what you said, Ed, with multi-phase extraction, um, to try and pull as much of that out as possible. It's going to be a function of, as well as the hydrocarbon fraction, carbon. The one thing we really can't control is what the desorption out of the soil phase is with, so depending on the hydrocarbon fraction and the goals, there's an upper limit to everything, right? But we have worked on quite a few sites that have NAPL, but it's going to
Yeah,
depend
so
on fraction and the goals, really. Yeah.
yeah, yeah. So the question really had two parts. Is it possible? And the answer is yes, it's absolutely possible. Is it
Mhm.
wise? That's site specific.
Is the complex carbohydrate addition varied for each site, or is it fixed for all petroleum remediation sites?
The answer is primarily yes, it's fixed. We do pretty much the same thing, uh, but not always. You can vary it. It depends on how long you need that complex carbohydrate to last. So as you do the calculations, you're looking at the site, you're looking at the site goals. You may vary the complex carbohydrate based on
Mhm.
persistence over time, also based on what you think you need initially. So some complex carbohydrates are more water soluble or break down faster than others. So it's a yes and no answer, primarily yes.
Yeah, and just to add, I guess, onto that as well. I mean, there is an upper limit because, from an actual implementation standpoint, there is an upper limit from a slurry density standpoint that you can actually apply, and that's when you're working in these heavily impacted areas. We're trying to balance that out as well. We can't add as much, we can't, put in as much carbon and calcium sulfate if we're adding that, and starch as we want. There's an upper limit. So we have to balance that out as well. And all that comes down to the, site specific design for each site. Okay. Ed, you said that the Boss 200 bacteria contain yeast and fungi. Can you elaborate? Why? I guess why, and then can you elaborate?
Yes, heavy hydrocarbons respond very well, or fungi like heavy hydrocarbons, though they tend to not be real happy about living in an anaerobic environment. So they will end up in the phase between the aerobic and anaerobic area, and there they contribute significantly to biodegradation. Yeast is similar, right? You're not going to produce a lot of yeast in a purely anaerobic environment. Well, that's not really true. Let me back up. The yeast that we're going to put in, we expect most of it to also be in that um, interphase. And the primary purpose of the yeast is the production of B12. And so that was an example of giving the vitamins that are needed. And that's the live yeast, right? So if you put yeast extract in, which of course is not live yeast, that is also for various vitamins. And I don't think that's what they were asking. They were asking about the live material.
I believe so. I
Yeah.
believe so. Okay. Next question. Is the COC mass present in the soil the driver for how much activated carbon and TEAs are needed?
Yes. Yeah, I think that's a pretty simple question. When it really comes down to it, most of your mass is bound to the soil and aquifer materials. It varies by geology to what percentage that is, but yes. And so that's kind of the little, the monster under the bed, so to speak, the hidden problem that you don't see necessarily in your monitoring wells.
Right. And yeah, just to just to add to that, I mean, what we have to account for in our designs is what we feel is going to be uh, come from the sorb phase into the aqueous phase in the time frame that the remediation, in that remediation window, right? So if you've got an F2 or like a diesel, well, obviously that's a lot of that based on, the high KOC values. You're not going to get a lot of that desorbing into the aqueous phase really in any time period unless you did something like a surfactant or some sort of heating or something. And so we don't always have to account for all of the mass because all that mass is not going to be degradable or, available to be sorbed onto the carbon. So the lighter hydrocarbons, that is going to shift a little bit, but the heavier it gets, we don't, have to account for it because it's not going to ultimately be available. So let's see here. We have a couple more. Do you recommend the injection of BOS only in the saturated zone, or is there a benefit to inject in the vadose zone?
Yeah, I think most of your value is going to come in the saturated zone. You can inject in the vadose zone. It's going to vary with geologies of how realistic that is, because water is needed. If you have a very, very dry vadose because of the kind of geology you're in, then you may have to supplement, provide some kind of water. All your physical transfers based on water. All your microbes require water to live. So, and all vadose zones are not the same. And so that kind of combine those elements together to get the correct answer. A lot of the eastern part of the country, you can probably inject in the vadose zone and get some value. In other parts, you're going to have to supplement with water if that's what you're going to do, if that's what your site requires.
Mhm. Yeah, the other, I guess, option, I mean, if you're talking about a true vadose, really true unsaturated, soil mixing, and you can, like Ed said, you can, if you available to you to soil mix in an amendment like BOS 200, and then you can lay piping in to help infiltrate water down through that, like that would be a potential option. But I'd agree with that, especially the shallower you get to, and from the injection standpoint, don't have that, hydrostatic pressure really helping keeping the injectate in. So distribution is a lot more heterogeneous in the vadose zone as well. So, excuse me. Well, thank you everyone for your questions. There are a couple more. We are out of time. I want to keep this under an hour. Ed, do you mind clicking to the next slide? So your contact information is up. Okay. So there goes Ed's contact information. Those of you that received emails from me, you have my contact information as well. As I mentioned, the webinar is being recorded. It will be posted probably early next week, so you kind of take a look at that. Again, there's a couple questions that have come in, and we'll go ahead and follow up with you directly on those. But I just want to thank you, Ed. I'll let you kind of close this out here.
Well, I appreciate everyone coming to this presentation today. If there's anything you're interested in or anything in this presentation which you saw that you think, well, I'd like to know more about, let me know and we can arrange a presentation for you at your office. Or maybe we can just launch it as a presentation like this for anyone who wants to listen. It'd be all up to you. So thanks for your time. Have a good day.
Thanks, everyone. Take care.